had proceeded to subdivide the two dimensional parameter space into compartments by the logic that we will divide in such a way that in each compartment a specific type of fixed point hits the border and turns into another specific type. So, what we had done was to divide the parameter space as depending on, this was your tau L axis and this was your tau R axis, and these values were 1 plus delta, this would be tau R, this is okay. This was the gross division. In between there would also be these subdivisions depending on which you decide whether it is a spiral or a regular fixed point. So, this is at 2 root delta r, this is minus 2 root delta r, this is minus 2 root delta L and plus, and we had decided that in this compartment a stable fixed point hits the border and remains a stable fixed point. In this part of the parameter space a unstable fixed point hits the border and remains unstable fixed point. So, these are the situations where there is no really change in the stability status. We had also decided that in this part, can you see in this part where the tau r is below 1 plus delta r and tau L is above 1 plus delta L, in that part you will have a birth of a pair of fixed points. We had called it the border collision type saddle node bifurcation or border collision fold bifurcation, and we decided that in this part here we have a stable fixed point coming hitting the border and becoming an unstable fixed point. What type of unstable fixed point? It is below this, that means your tau r is less than 1 plus delta minus 1 plus delta, that is it will be a flip saddle. So, turns into flip saddle. So, last time we were discussing this part, before we broke off we were discussing this part, and since a stable fixed point comes and hits the border becomes an unstable fixed point, the natural question is will any high periodic orbit become stable, and we started the discussion with period 2, and we had seen that this stability is given by the fixed points, the period 2 fixed point, that means in the parameter in the state space there is one fixed point to the left, another to the right. So, this point maps to this point and this point maps to this point. We had called it x star to L and this point was called x star to R, right, and we had obtained the values. It can be easily obtained. I had written the values as x star twice L is equal to minus mu 1 plus tau r plus delta r divided by tau L tau r minus 1 plus delta L, and it will be good exercise for you to do it yourself. These are rather easily found, because all you need to do is to start from a point here, map it to the left, to the right, again from here map it to the left, and that way you obtain this point whose stability you have to obtain. So, your x star twice r it would be obtainable just by simply changing the L's to R's and vice versa, 1 plus tau L plus delta L divided by tau L. This is already symmetrical, so nothing has to be changed. And that on that basis we had proceeded to at least try to infer about this existence of this period 2 point. See, we are talking about this range. In this range, the condition is tau L is between minus 1 plus delta L and tau R is less than, right, that was the condition. Now, if this condition is true, then what is this particular number? It is negative. Okay. See, this says that this term is negative, and this term is by this positive. Yeah. So, this term is positive. Okay. So, obviously, take into account this term is negative, this term is positive. Now, consider this term to be negative first. First consider this term to be negative, that means 1 plus delta L, 1 plus delta R is bigger than tau L tau R. This term is negative. If this term is negative, the denominator is negative, negative, negative cancels off. So, the sign of this depends on mu and this fellow is negative. So, when mu is positive, you need this to be here in the negative side. No, it is not related to stability. It is not related to stability. We are talking about the existence. We had obtained the existence condition, not stability condition. Okay, because as yet we are not talking about the stability at all. Right? Stability will depend on something else. I will come to that later. So, pay attention. This is negative. This is positive. This fellow is so. Then, if this fellow is negative, for what value of mu will this fixed point exist? Positive. Then this term will be negative and this term will be positive. So, for the FP exists for mu positive, right. If tau L tau R minus right, only when this is true, then this is true, else what happens? If this is positive, then it exists for mu positive, no, mu negative, yes, mu negative, right. So, the fixed point exists for mu negative if the reverse is true. So, this particular equation would be quite similar to what you have seen earlier in the one dimensional case. It will be something like this. This equation, it means that if you take a point somewhere here, then the period 2 orbit will exist after the border collision. That means, you would anticipate something like, from theory you will anticipate something like this to happen in the bifurcation diagram. And then a period 2 orbit will That means, for mu greater than 0, this fellow will exist, period 2 orbit will exist. I cannot as yet commit whether this fellow will be stable, because we have not yet considered the stability condition, but at least we are sure that this fellow will exist. But what about this part? What about this part? Here the stable fixed point, stable period 1 fixed point came and hit the border, but the period 2 orbit was existing in the same side, right. Period 2 orbit was existing in the same side, and so period 2 orbit was existing in the same side. Therefore, the behavior will be will that periodic orbit be stable or unstable? I do not know, I have not talked about that yet. So, for the present time I will mark that with like this, but we will later clarify that issue. Okay. So, here the period 2 orbit is in mu for mu is equal to 0 when this is true, else when this is true. Okay. Clear? Good. Now, let us consider the stability condition. What Sahitya was talking about, let us consider the stability condition. The stability condition is where you have one point mapping to this point and then it is coming to this point. So, what is the stability of this orbit? The stability of this orbit will be given simply by, here is a matrix that maps to here and then comes back here. Therefore, this matrix times this matrix, its eigenvalues. So, we will have to talk about the first Jacobian matrix is JL say and JR, that one, which is tau L1 minus delta L0 times tau R1 minus delta R0. This I gave you the last time. Have you done that? It will be tau L tau R minus delta R tau L minus delta L tau R, and its eigenvalues would be a big one. The big one I have given you the last time. I will not give you the same big one today. Instead, I asked you to simplify that. If you simplify that, that simplification is rather simple, because what you had was eigenvalues would be half tau L tau R minus delta L minus delta R plus minus root over tau L square tau R square. This you can easily get simply by putting this equation into a symbolic computation program like Mathematica or Maple and ask it to give the eigenvalues. Rather simple stuff. Minus 2 tau L tau R delta R. I am doing this because you have to be used to such manipulations. Minus its symmetrical thing 2 tau L tau R delta L plus delta R square symmetrical plus delta L square plus there would be minus 2 delta L delta R, this whole thing. So, this continues. Now, if you simplify this, the condition for stability is this fellow is equal to plus 1 or minus 1. Okay. Say I consider it equal to plus 1, then how I will manipulate it? I will bring this 2 here first, then I will bring this fellow here first, then I will square it and then cut off, many things will cut off, and then that simplification will ultimately lead to something very simple. That is what I asked you to do. Now, if you do that, you will find that the conditions simply boil down to right. So, the condition will ultimately boil down to, there are two cases, +1 and -1. So, for this can be, this has to be less than +1, then the condition would be tau L tau R less than and the other condition is smaller one should be greater than -1. That gives you tau L tau R greater than -1 minus delta L. Okay. Now, notice that we already have come across this fellow, because when we talked about the existence, your denominator was so when we said this term less than 0, see this term less than 0 means this term is greater than this. So, this is the condition. So, stability condition is essentially the denominator of this equation. What does it mean? It means that when we talk about this point, it is not only existing but also stable. But here when we talk about this point, it is unstable. So, the period 2 fixed point that was existing for the same site mu negative, but that would be unstable. So, now we have decided that this diagram that we drew, this orbit must be an unstable orbit. Okay, because its eigenvalue would be greater than +1. Obviously, there is another condition which is this. Violating this condition, this fixed point, this period 2 fixed point will become unstable. It will continue to exist, but it will become unstable. Where is that? When this is satisfied, when this becomes equal, and that equation again we can anticipate from what we have learned in the 1D case would be something like this. This kind of a line. So, in this range we can expect the period 2 orbit to actually occur. Here it will not occur because it firstly it is a subcritical period doubling. This is a subcritical period doubling. And this is a supercritical. Again, like we discussed in the case of the 1D, here these two orbits emerge at acute angle, not the 180° angle. Here also is so. So, this fellow has become unstable. Let us try to understand what actually happened in physical system in this case. If any physical system encounters this kind of a bifurcation, what will happen actually? A stable periodic orbit was there, it hit the border, and then beyond that the period 1 orbit is unstable, period 2 orbit does not exist, and actually then the system will collapse. So, that is a collapsing condition. Again, this subcritical period doubling and whatever we are inferring about that, that refers to only the close linear neighborhood of that border crossing fixed point. So, in that sense it will go to infinity, but that does not mean that globally it will go to infinity. So, in the local sense it will go to infinity. In this case, it is system is will actually collapse.
Then how will you conclude that hierarchy orbit may
Well, I can come to that. Yes, Yes, you have a question. His question is that how do you make sure, how do you be sure that a higher periodic orbit will not be existing? Yes. So, we need to understand where will the higher periodic orbits will exist. Let's look at that. So, when we talk about the higher periodic orbits, which is the one that we consider first? We should consider first period 3. Okay. So, let us consider period 3. And when we consider period 3, then what kind of orbit will you consider? Notice, in this part you have got a okay, let's formulate the argument this way. In this part, the tau L is between minus 1 plus delta plus 1 plus delta, and therefore it was stable, right. So, in this part it was stable, in this part it was unstable. So long as mu less than 0, we do not really need to bother about it, because I know that the period 1 fixed point is stable. So, we are considering mu greater than 0. When mu is greater than 0, then what is the status of the fixed point that was actually obtained from the left hand side equations? We had said no, there was a x L star which for mu greater than 0 will be in the right hand side. For mu greater than 0, it will be somewhere in the right hand side. It is a virtual fixed point, but that fellow is now an attractor. So, any initial condition to the left, we will see there is a attractor sitting there somewhere. So, it will be attracted to that. So, successive iterates will approach that actually non-existent fixed point. So, you can expect this kind of orbit to be there, and finally, it will try to approach that. But the moment it comes here, it encounters what? In the right hand side, it is a flip saddle, and it will flip. Okay. If it flips, it goes to this side. Okay. But in this part, there is a regular flip, there is a existing fixed point. So, suppose the fixed point is existing here, and this fellow is mapped here. What will happen? It will flip to the other side, and as a result, it will come back here. So, you can see that when we consider a period 3 orbit, it was possible to consider a L orbit. L is this side, R is this side, or R orbit. But out of these two, it is more logical to consider a LR orbit, because I can see that you can have more number of iterates as this fellow approaches this virtual fixed point. This is x L star bar, bar means virtual, and suppose here we have the x R star. But the moment it comes to the right hand side, it flips to the left, and therefore, we can anticipate that we should logically consider an orbit that is LLR orbit, only one point in the right hand side. So, how we will obtain the existence of that? His question is, how do you know that the period 3 orbit does not exist? Yes, sure. So, we will consider an orbit something like this, a point here, another point here, and one point to the right, and it will map in this way. Right. So, in considering that, we can easily obtain all the 3 points. What we will do? We will start from this point, apply the left hand map once, apply the left hand map another time, and come back here. Apply the right hand map and come back here. Then we will say x n plus 3 is equal to x n, y n plus 3 is equal to y n. Solve the equation, you will get the fixed point here. Similarly, you start from here, apply the left, then right, then left, do the same procedure, you obtain this point. Start from here, all this can be done relatively easily by hand. It is not at least up to the period 3 is not all that difficult. So, once you have obtained that, then what do you do? Once you obtain this, you would notice that we are trying to consider when this fellow will exist. Existence means this point should be in the left, this point should be in the left, and this point should be in the right. Is it possible for this point to hit the border before this point? Obviously, this point was mapping to the border, mapping to the right, and this point was still mapping to the left, and so if anything hits the border, this fellow should. So, we should actually consider this fellow's x coordinate, x coordinate of this fellow, and that is what will actually determine whether this fellow is in the left hand side or right hand side, or this periodic orbit exists or not. What about this? Can it hit the border? If it does, say it moves to this side, I would have to say that there is a period 3 fixed point with all the points in the left, which is not possible, because each side is a linear side. So, in a linear system you cannot have a high periodic orbit, so you cannot have period 3 also. So, the critical situation is here, this fellow hitting the border, and that condition can be you can easily obtain it as, you have got a 1 plus tau L minus delta R plus tau L tau R plus delta L delta R plus tau R delta L whole times mu divided by 1 plus delta L square delta R plus tau R delta L plus delta R tau L plus delta L tau L minus tau R tau L square. This should be less than 0. Well, now if you actually substitute the parameter values, like say take delta L delta R both to be 0.5 or something, the determinants, these are dissipative systems. So, consider both sides to be having determinants to be less than 1. If you substitute that, then you will find that this fellow does not occur, this particular thing does not occur to the left of this, it always occurs to the right of the period 2. So, it will occur somewhere here. So, this is one that is obtained from the existence. There is another condition of stability, and what is stability condition? Stability condition is obtained by Jacobian of the left times Jacobian of the left times Jacobian of the right. Its eigenvalues should be less than plus 1 and greater than minus 1. That is the condition. Now, that condition, this condition again you will find that this is same as the denominator, but this condition gives an additional thing. So, you get 2 contours, 2 extremities, and that defines in which range the period 3 orbit will actually occur. Similarly, the process that I have just outlined, you can apply that same process, same logic to the period 4, to the period 5 and all that, and you can find that there will be distinct ranges where these fellows will exist. So, again, as we saw in the case of the 1D, if you increase the parameter like so, you will find a period 2 orbit, in between there is nothing, again a period 3 orbit, in between there is nothing, here is a period 4 orbit, in between there is nothing. Is it possible? No, because here there is no scope of this fellow going to infinity, because as you see that because of the existence of the unstable stable attracting fixed point in the right, any point to the left cannot go to infinity this way. It will see an attractor and move always to the left. Any point to the right will flip to the left, and therefore, it cannot go to infinity. If it cannot go to infinity, then obviously something will occur, and that something is, if none of these periodic orbits are existing in this part, this will be chaotic. So, period 2 chaos, period 3 chaos, period 4 chaos and all that, and that way it will reach this point. So, you can anticipate a similar type of period adding cascade as you increase the parameter this way, the type that we saw the last day on the computer, but that was for the period a one dimensional system, but for the two dimensional system also a similar situation will occur. The only complication is that there can be overlap. There can be overlap between these orbits. As a result, there can be coexisting attractors, something that does not happen in 1D case. In a two dimensional case, these ranges of existence and stability where these fingers actually occur, they may overlap, and when they do, there would be a range in which both period 2 and period 3 occur. There may be a range where period 3 and period 4 occur and all that, and in those parts you will find coexistence of attractors. Clear? It is also possible to have coexistence of aperiodic orbit and chaotic orbit. So, there is a lot of complication here. Let us not go into that complication. Essentially, we understand that under such situation we are likely to see a period adding kind of cascade. Now, let us understand this part. This part we know. What happens in this part? A period 1 stable fixed point and a period 1 unstable fixed point are born. So, it is like a saddle node bifurcation, simple. But in this part what happened? In this part what happened? Let us consider this part. What is the condition? The condition is in this part tau L is above 1 plus delta L and tau R is below minus in this condition, when in the last class, I do not have the slides here, but when in the last class we derived the condition for that to occur, that means two fixed points are born, that condition is satisfied here. But now, since both the sides are unstable sides, both the fixed points are unstable. So, two unstable fixed points are born. What will happen? To see what will actually happen, let us draw the character of the state space. Two fixed points are born. One say is here and another say is here. Okay. Both unstable. This fellow is a regular saddle, this fellow is a flip saddle, that is all. Because one is greater than this one, condition is regular saddle, this fellow is flip saddle. If you have a regular saddle, you can draw its stable and unstable manifolds. So, the stable and unstable manifolds will originate at the eigenvectors. So, at this there will be an eigenvector like this and there will be another eigenvector like that, say. Say this is the stable eigenvector and this is the unstable eigenvector. Now, a very important point pertaining to non-smooth systems, something that I did not talk about so far. How will this unstable manifold proceed? The unstable manifold will proceed along this, and unstable manifold has the property that any initial condition on the unstable manifold will remain on the unstable manifold, that is the definition. So, this point will map, this point will map, it is irregular. So, it will map like this, but it has come here and it has continued, but then this point when it maps to another point here, it maps by the left hand side map. Here also it maps by the left hand side map, but here it maps by the right hand side map. Now, where does this point map to? We have already seen while we were deriving the map for this normal form that any point on the y axis maps to the x axis. So, this point must be mapping to this straight line here. So, this point must be mapping to this point. Any point to the left should be mapping by the left hand side map, any point to the right will be mapping by the right hand side map, and therefore, obviously, the slope after this point cannot be the same, it will have to fold. Is that logic clear? Because this point is mapping to here and this point is mapping to somewhere here, this cannot continue the same line because you are now using a different map, different linear map, and so this will have a different slope, must have a different slope. It means that the unstable manifold will fold at its intersection with the x axis, okay. And then this fold point will again map to some point, will again map to some point. So, suppose this one continues and at this point maps to this point. Since this is a fold point, this point also must be a fold point. So, it will also fold, clear. So, all the forward iterates of the fold points will be fold points. So, the unstable manifold folds at the intersection of the 45-degree line with the x axis, and any forward iterate of a fold point will be also a fold point. So, that gives a very complicated folded structure to the unstable manifold. What happens to a stable manifold? Just the opposite, because what is the definition of stable manifold? It is that the stable manifold approaches that fixed point, and therefore, by the inverse map it goes away from the fixed point. So, if you imagine the inverse map, its character will be the same as this, okay. Fine. So, only the point is that if any point on the y axis normally maps to the x axis, by the inverse map any point of the x axis will map to the y axis. So, by the same logic, this fixed point, this stable manifold will fold at its intersection with the y axis, okay. Is the point clear? Because you are actually applying the same logic, but applying by replacing the forward iterate by the backward iterate, and while you take the backward iterates, then x axis maps to y axis. So, the logic that we said that, okay, the moment it crosses the y axis, the slopes are different, and since the y point maps to the x point, and therefore, it will have a fold in the x axis, the whole thing happens on the y axis, okay. So, this fellow will fold at the y axis like this, okay. Clear? So, there is a structure given here. Now, you notice that okay, after this point is understood, let's talk about the similar stable and unstable manifolds of this fixed point, which are this is flip fixed point. What will happen? This fellow will also have a stable and unstable manifold. Say this, the unstable manifold is like this, and the stable manifold is like that. Then what will happen to this unstable manifold? No, the stable manifold will, oh, this will be a stable manifold, sorry, and this will be the unstable manifold. So, the stable manifold will have a slope like this, and it will fold at, no, it will not fold here, it will fold here, stable manifold. Unstable manifold will fold somewhere here on the x axis. Good. But then this unstable manifold and a stable manifold, they have some slopes, and that slope can be easily understood. Why? Because this slope is nothing but the slope of the eigenvector. So, when you if you give this matrix to a program like Mathematica or Maple and ask it to obtain the eigenvector, it will give the eigenvector slope, and you will find that the slope of this one, the stable eigenvector, its slope is minus delta r divided by lambda 1 r. 1 is for the first eigenvector value and r is for the right hand side. So, this slope is this much, and the other one, the unstable eigenvectors, its slope is so determinant by the eigenvalue itself, that is the slope of the eigenvector. We are considering condition where this is true. So, the determinants are less than 1, we are considering the situation, and these are the slopes. It is not difficult to see that then this fellow will fold, okay, and no, this diagram will cause difficulty. Let us blow it up. Let us blow up here. We are considering the fixed point here, whose unstable manifold is here, and the stable manifold is somewhere here. The unstable manifold will fold here and like this, right, but the stable manifold will not fold here and it will continue, right, which means that at this point what do we have? We have the it must be, we have the intersection between the stable and the unstable manifolds, and whenever there is a intersection between the stable and unstable manifold, what happens? There has to be an infinite number of intersections. We have already seen that. This means that somehow these two manifolds will be convoluted, will be folded and go any possible way, so that there are infinite number of intersections. And we have seen that under such condition there is a horseshoe kind of structure, the existence of a chaotic orbit. So, this logic tells you this is the stable manifold which will fold here, again there will be intersection and stuff like that. There will be large number of intersections, infinite number in fact. And the logic behind the intersection is that here is a unstable manifold which will fold here, here is a stable manifold which is fold there, which will not fold here, which will fold here. So, the stable manifold has a larger slope by that value, and the unstable manifold has a smaller slope. Therefore, after the fold there has to be an intersection, there must be an intersection. Therefore, there must be a chaotic orbit because of this intersection. Okay. Good. This is all very well understood. Now, there was another fixed point sitting somewhere here. What will it do? No, what will it do? Its unstable manifold was coming like this, and its stable manifold was coming like that, and the unstable manifold will fold at the intersection here, all right. But you see, this is the unstable manifold and this is the stable manifold. This unstable manifold then has an intersection with the stable manifold of this fellow. Okay. The unstable manifold here will have a stable manifold of this fellow. What is the consequence? We have, while we were talking about the smooth map, then also we have treated this problem. Suppose there is a saddle fixed point, it will have a stable manifold and it will have an unstable manifold. And suppose any line intersects this stable manifold, any line, then what will happen? This line, you can take the forward iterate of this line, means all the points are iterated by this map, it will map somewhere. Because it is a stable manifold, there is a contracting direction like this, it will, in the successive iterates, it will approach the unstable manifold here, and finally asymptotically it will converge onto the unstable manifold. Okay. Now, here notice what is happening, we have the same situation here, here is a stable manifold and this line has intersected with the stable manifold. Naturally, the immediate conclusion is that this unstable manifold will asymptotically converge onto the unstable manifold here. They will ultimately become one and the same unstable manifold of the system, though they initially started out as the unstable manifolds of two different fixed points. Okay. Now, in any system, all the iterates are attracted to the unstable manifolds. We have seen that. We have seen that. Just to refresh your memory, if you have a orbit like this, if you have a point here, initial condition, where will it go next? Where will it go next? It will be attracted to this side because of this stable manifold, and it will go to there. So, it will ultimately go like this. Ultimately, you see it is coming closer and closer to the unstable manifold, and it is going away and away from the stable manifold. So, the unstable manifold ultimately act as the attractor. Now, here we have a situation where the unstable manifold, there are two unstable manifolds and both point to the same thing, a chaotic orbit here. Both point to the same thing, a chaotic orbit. So, it will ultimately land as a chaotic orbit, and because in the state space the initial conditions are attracted to the unstable manifolds, which ultimately all lead to the same structure. Here there must be a chaotic orbit here. This chaotic orbit is unique. You cannot have another orbit. It must be unique. It is to be unique chaotic orbit. Well, will it be stable? Well, stability condition is different. You already know that if there are there is a fixed point here, there is another fixed point here, and suppose there is a this is something stable. So, some orbit here, some orbit there, and in between there is a regular saddle fixed point sitting with the stable manifold here and the unstable manifold there. Then we have already learned that the stable manifold acts as the basin boundary. Each will have its basin of attraction, this will have its basin of attraction, and the separator will be the stable manifold. Why? Take any point to these two sides, they will be asymptotically going away from each other. So, the stable manifold act as a repeller, it will actually divide the basins of attraction. We have learned that. Here also the same thing will happen, but that requires a regular saddle. Here we have a regular saddle. So, its stable manifold will divide the basin of attraction. One is here, all right, the other is at infinity. So, any initial condition here actually goes to infinity by the action of this unstable manifold, it goes to infinity. Any initial condition here also goes to infinity, initial condition here also goes to infinity. So, there is an attractor at infinity, there is an attractor here, and they coexist, and they are divided by this stable manifold. This is the dividing boundary, right. And most interestingly, this fellow folds like this, right. We have seen that the stable manifold will fold. See what happens then. We have got a situation where this orbit comes and hits it, and we know that this leads to the attractor. We also know that this fellow folds and comes here. In case this is bent like this, then it will intersect the stable manifold before it folds. So, it will intersect the stable manifold before it folds, means the unstable manifold and the attractor existing on the unstable manifold will then go out of the basin of attraction. It is a boundary crisis, and you can easily obtain the condition for the boundary crisis. You know the slope here, you know the slope after it bends, naturally you can find this cutting point. You know the slope here, you can find this cutting point. This orbit will be stable so long as this point is to the left of this point. Okay. So, here also you can by logic obtain in closed form the condition of existence of this chaotic orbit. We had obtained that, remember, in case of the 1D system. We had obtained that, you could obtain that, it was very simple. In this case it is lot more complicated, but nevertheless it can be obtained, and it yields an equation that is also quite similar. It's like this. In the 1D case we had obtained this, but its condition was very simple, but in the 2D case that condition is relatively more complicated. It is delta L tau r lambda 1 L minus delta r lambda 1 L lambda 2 L plus delta r lambda 2 L minus delta L tau r plus tau L delta L minus delta L square minus lambda twice L delta L, that has to be greater than 0, then it is stable. Now, this condition may be looking formidable, but I have explained how it is obtained. So, I will give you the exercise that you have predicted what will be the behavior in all these parts. Take a suitable value of the determinant, say determinant to the left is say 0.7, determinant to the right is also 0.7, both dissipative, and then you take the values of trace in the left and in the right in such a way that once this condition is satisfied, vary mu and see what happens. Your prediction is that it will cause a period doubling, in this part period tripling, in this part period 1 to period 4, and so on and so forth. In this part period 1 to chaos directly, in this part nothing to chaos, because at this point a period a couple of periodic orbits are born, period 1 orbits are born and both are unstable. So, born means it is not existing before mu is equal to 0. So, in this part you will expect that the periodic orbit will be born. Now, if you want to write the program to obtain the bifurcation diagram, for mu negative it will run to infinity and your program will collapse. So, you will have to start from mu positive and see what happens if you reduce the mu. You will find a chaotic orbit slowly shrinks and becomes 0, and then it vanishes. Okay. These things you should yourself try out by writing a program. This program is rather simple. You could also use one of the existing programs, no problem, but it is always advisable to do it yourself to convince that yes, that is what happens. Okay. So, we have more or less covered these parts. There is, as I told you, that this part looks simple, but there is a lot more complication to that, which I will come to later. That is what I will come to in the next class. Okay. So, that is all for today.